look here, right after this one small observation you can see. So here is the big thing I want you to get away from. So I know the limit is defined as this epsilon dot language, which means if I want to find a limit of function using this epsilon dot language, it's not going to be very straightforward. All right? So I have to argue this by epsilon delta, and because this epsilon is chosen arbitrarily, so arguing based on this definition is not going to be an easy job. Are you with me? However, if I know this function is continuous, then finding the limit will be extremely easy. Okay? If I know this function is continuous at a given point, then the limit of the function at this point is nothing but the function value at this point. All right? As long as I know this function is continuous at this point, then finding the limit will be extremely easy. Are you with me? It is nothing but the function value at this given point. And luckily, all the functions we know are all continuous, which means we can use this principle for pretty much every function we know. Okay? So especially, we know the polynomial functions, the rational functions, so the trig functions, the log functions, the exponential functions, etc. Most of the functions are all continuous in their domains, in their natural domains, actually. Okay, so this is a very, very important thing. You don't have to verify this, but you can use this condition. Pretty much all the functions we will see in this class are all continuous in their natural domains, which means as long as I know a point is coming from its natural domain, then evaluating the function at this point will be exactly the function value at this given point. Are you with me? So I will give you one example. And this will be what you will see in your homework and so on. So 5 minus 5. 9x squared minus y squared. Okay, so we want to evaluate this polynomial function at a fixed point 5 minus 5. Again, I want to stress, when you want to find the limit of a function, you have to have a point to begin from. Okay? So this fixed point is 5 minus 5. So I'm asking the limit of this polynomial function when the points x, y are approaching 5 minus 5. Think about it. If you want to argue what the limit is by using this epsilon dot language, it's not going to be easy. You have to evaluate the difference between this function value with the function value at 5, this function value and some function value we find, this capital L. And then you have to argue if the points are close enough, then the function value will be close enough to this fixed value you found in the very beginning. However, as long as I know this is a polynomial function which is continuous in its natural domain, what is its natural domain? What is its natural domain?
0 to 1.
It's all the two-dimensional plane, R2, am I right? It's all the R2. As long as it is continuous on the whole natural plane, I know this point is in R2. Then what I do? Just plug in this formula. It's going to be 9 multiplied by 5 squared minus 5 squared. Okay? It's going to be 200. So the only thing I did is to check this point, this fixed point, is in its natural domain. And then I just do a plug-in. Okay? This will be the main theme of the whole lecture. Super easy. After class, you don't have to remember anything here, but you have to know how to evaluate the limit of a function for a given point. Eventually, we'll go to a more complicated function, but this principle will be exactly the same. I want to find the limit of a function when xy approaches minus 3, minus 2 for this rational function. 4x squared minus 3y squared plus 2x squared plus y squared minus 4. Okay? So this is a rational function. So naturally there are restrictions related to rational function. And that restriction is x squared plus y squared minus 4 is not equal to 0. You can indeed solve this inequality and find the domain of the function, right? So the domain of the function has to be all the R2 deleting, what do you have right here? Deleting a circle, am I right? Deleting a circle, x squared plus y squared minus 4 is equal to 0, defines the circle centered at 0, 0 with radius 2. So basically the domain of the function is a region in R2 where you have to delete one single curve. All the points, as long as these points are not on a circle, will be in the domain. Are you with me? So you can check this point is in your domain or not. One way to find this point is in the domain or not is to write down what the domain is and then check whether this point is in your domain. All right? Are you with me? And actually, an easier way to check whether this point is in the domain or not is just to plug in and see whether it's 0 or not. Are you with me? You don't even need to find the domain. You just plug in this denominator and see whether it vanishes or not. You don't want it to vanish. As long as it doesn't vanish, it is exactly in the domain. All right? And we know the rational function is continuous in its natural domain. Okay? So as long as this point is coming from the natural domain, the function has to be continuous at this given point. And because it is continuous at this given point, then the limit of the function when it approaches this point will be exactly the function value at this given point. So in summary, what we can do is just to plug in. Okay? So we plug in, this is going to be 4 multiplied by minus 3 squared minus 3 minus 2 squared plus 2. Then you have minus 3 squared plus minus 2 squared minus 4. In the end, you're getting a 26 divided by 9. Okay? So numbers are not complex. The only principle for the first half of the lecture is to check whether the given point, the fixed point, is in its natural domain or not. If it is, everything is nice and easy, you can just plug in the numbers and evaluate the function. Okay? So we'll do a couple of more examples, and then we will go to the harder question of what if the limit does not exist. Okay? So let's do a couple of more evaluation. So I want to do limit xy approaches e squared 9 log square root of xy. Okay? You have square root, you have a log. So naturally, there is a restriction coming from the formula. All right? Which means you have to require xy to be strictly positive because you have a log right here. So this one has to be strictly positive. So you can go to R2 and find the region of where xy is strictly positive. What does xy is strictly positive means when you translate back to that R2 plane? First and third, all right? It can be both positive or both negative. So this is actually the domain of the function as 2 pieces of regions. Combine them together. This is the domain of the function. You can check whether this guy is in the domain or not by simply observing positive, positive. So this guy has to be in the domain. An easier way of doing this is just plug in here and see whether this is well defined or not. Right? That will be a much easier way to check. You can plug in e squared 9, everything's positive, so the whole thing is well defined, so it has to be in the domain. So what we can do is just to plug in. So it's log square root of e squared multiplied by 9. You can do a couple of simplification involving square root and a log. What do you learn before? So the square root can be easily translated into e squared 9 to 1/2. Am I right?
Yeah.
So as long as this is a power together with log, I can bring down as this coefficient. Am I right? Have you learned this before? The properties of logarithm functions. So e squared multiplied by 9, and this is a multiplication together with a log. It's translated into addition, all right? So e squared plus log 9. So log of e squared is just a 2, all right? So this is going to be 1/2 2 plus log 9. So in the end, you're getting a 1 plus half of log 9. Okay? And that's it, right? Just check a point is in the domain or not. I want to have one slightly more involved question, and we will call this a net for if the point is in the natural domain. So this is one additional question I want to evaluate. So I want to evaluate the limit of a function when the point approaches 18.3, x squared minus 6xy divided by x minus 6y. Okay? Okay, so this is slightly more complicated than before because the point falls outside of the domain, right? When you plug in 18.3, the denominator is equal to 0, so it's not going to be in the domain, right? It's not going to be in the domain, but if you look at the numerator and the denominator, there are some common factors. You can simplify this fraction, right? This can be simplified because you can factor the numerator by x, so it's x minus 6y divided by x minus 6y, all right? You can do this. I haven't done anything about the evaluation yet. I haven't evaluated the limit at all, okay? And I can factor out the numerator. Now I'm going to remove the common factor. I'm going to remove the common factor here, and making it to be just a very easy function x. The only thing I need to do is to justify why I can remove this common factor. Okay, so the only thing I need to justify is to why I can remove this common factor. Okay? You can remove the common factor if it is not equal to 0. All right? It can be positive, it can be negative. If you have this common factor which is not equal to 0, then you can remove this common factor. This common factor is never equal to 0 in the whole evaluation of the limit for a very simple reason. Because when I define what the limit is, I fix the point, and then I let these neighboring points to approach this point. But throughout the whole process, I never require this xy to be exactly equal to this number, all right? So this point is never equal to 18.3, and it is in a small neighborhood of this fixed point. I can make sure this factor is never equal to 0, all right? I can make sure this guy is never equal to 0. So indeed, I can remove this common factor because when you define a limit, this xy as the neighboring points are never equal to this fixed point. So you don't need to worry about the domain issue anymore. Are you with me? So I can remove this common factor. Now I'm just evaluating the limit of this polynomial, which is exactly equal to 18, all right? Which is just equal to 18. So this is one slightly more complicated question, but it still falls into our evaluation of this simple fact. But you're looking at this function rather than the original function, okay? Questions? Okay, now we're going to look at the more complicated questions where you still have this domain issue, but you cannot simply resolve this domain issue by removing the common factor. Okay? You can easily design your own fractions where the fixed point is not in the domain and there's no common factor to remove. So let's look at this function. Limit xy approaches 0, 0, x plus 2y, x minus 2y. Okay? So in this particular example, you still have the domain restriction. And when you plug in this fixed point 0, 0, the denominator vanishes, so 0, 0 is no longer in the domain anymore, which means our first principle does not apply here. All right? Does not apply because this point is not in the domain. Or if you plug in this 0, 0 in this whole fraction, it doesn't really make sense anymore. Right? It's going to be 0 over 0. It's not even well defined. However, we can still evaluate its limit at this given point 0, 0, and we can indeed verify whether this limit exists or not. Okay? So next, I want you to be able to do is to prove a certain fact, which is the limit does not exist. Okay? So before I do that, I actually have one small remark to make. Okay? Listen to me carefully. If a point is not in the domain, it does not necessarily mean the limit does not exist. That with me? It's only you cannot use continuity to evaluate the limit. That with me? So I know a fixed point is not in the domain. This can be easily checked, but I do not necessarily know whether the function does not have a limit or not. Okay? So I'm actually giving you an easier question. I just need to prove this limit does not exist. Okay? I do not want you to be able to do evaluation of a limit if a point is not in the domain. Are you with me? You can still have the examples where the point, the fixed point, is not in the domain, but the limit exists. It's only you cannot use the continuity anymore. So how can we evaluate the limit? So you have to use new methods to evaluate the limit if the point is not in the domain. Okay? So I'm actually giving you a much easier question right here. You don't have to evaluate the limit if the point is not in the domain. We are only proving that it does not exist, which means you don't need to evaluate at all. Yep?
Can't you take the natural log of that, and then you would end up getting e to the 0, which is 1?
You can take the natural log, but you're actually changing the function. Right? Introducing a natural log is going to change the domain.
But if you introduce it to there and to the limit, and you just solve for that, you get 0. And then if you change it back to like e, so it'd be e to the 0, which is 1.
But if you're taking a natural log, you're changing the domain of this function. The domain of the function is only x minus 2y is not equal to 0. But if you're introducing the natural log, you're requiring x plus 2y is positive, and x